All right, taking a look at chapter 4.6, limits at infinity and asymptotes. All right, so this is not necessarily derivative related. We won't be utilizing derivatives in this, section, but we are dealing with limits, okay? We'll do some stuff with limits and derivatives in a little bit. That's called L'Hopital's rule, but right now we're just kind of looking at limits. We're talking, I guess if you think back to like the shape of graphs, what we just worked on using derivatives, we then kind of go into this idea. What happens as you keep going farther and farther and farther in a graph? All right, so the limit, what a graph does, the y values of a function as you go really far to the right, to the left, right? Really what most functions go up really high or down really high. They are unbounded. They go to infinity or negative infinity. That's called their end behavior. Some of them level out, right? And these have what we call horizontal asymptotes, all right? So the first one we have, f of x equals 2 plus 1 over x. If we look at a graph of this thing, we'll notice, yeah, this graph levels out. Levels out on the right side, and it levels out to the left side. And it looks like it levels out, 1.4, 1.6, those y values, looking like it kind of levels out at a height of 2. If we keep going, we don't suddenly see another shoot up or something like that. It's just kind of stuck there, right? So the way that we can do this a little bit more mathematically than just looking at a graph is with limits. Now, I guess I will touch on this very quickly. Most of these are also going to have what are called vertical asymptotes, not the focus of today's lesson. We should know that vertical asymptotes, these up and down lines, happen when you try to divide by 0. And so in this case, we do get one at 0, x equals 0. So if I put 0 right here, I can't do 1 divided by 0. All right, but we're focused on the horizontal asymptotes, the stuff at infinity. All right, so you can do these by doing a table. Okay, so if we plug in things like -10, -100, -1000, notice what happens to these values of y when you plug in negative numbers that get much larger. We get 1.9, 1.99, 1.999. Now, I hope you're okay with the idea that that limit produces the value of 2. All right, and if we plug in +10, +100, +1000 to make a table, 2.1, 2.01, 2.001. All right, I hope you're with me that that also is +2. Okay, so that kind of confirms my idea that we have a horizontal asymptote here at y equals 2. All right, instead of using a table, we can try to just do this kind of mathematically a little bit. All right, so if we do the limit as x approaches either positive or negative infinity for this one, usually you should split this up into positive first and then negative, I guess. We can do that. The idea, you can't actually put kind of like infinity into a problem. Infinity is a concept, an idea. We think of it as a really, really, really big number, but we do have one major idea. Now, the laws of limits say that when you have two things added inside of a limit, you can kind of split it into two smaller ones. So this is 2 plus, the 2 doesn't have a variable, so I'm not worried about it. The limit as x approaches infinity of 1 over x. All right, so really it's this part right here that we need to discuss. Once we do this once, we really won't have to do it again. But the idea is when you do a bigger and bigger and bigger number into this little expression, 1 divided by something very, very, very large. All right, 1 divided by 10, 1 divided by 100, 1 divided by 1,000. That's where these decimals are coming from. You will eventually get 1 divided by something so, so, so big that your answer is very, very, very close to 0. And that is why our answer is 2. Notice we approach 2 a little bit above it, and then we approach 2 from below it based on a negative idea. All right, but the idea is still the same. Eventually you are adding, you're doing 2 plus something very, very, very close to 0. All right, so mathematically we can kind of just say 1 over x as x goes to positive infinity or negative infinity. This is negative, it's the same idea. 1 over, or any number, any common constant number divided by x as x goes to infinity or negative infinity will be 0. All right, so let's check this out. If we do sine of x over x, right, when we are in the positives, so the right side, notice we get like negative 0.05, negative 0.005, and then scientific notation to 10 to the negative fourth means 0.0008. Okay, so we get numbers that are getting closer and closer and closer to 0. All right, and on the left-hand side, if these are negatives, we actually get the same exact numbers. That's kind of fun. So again, we get very close to 0. Now let's talk about y. All right, sine of x. So these are both the same. So we're just going to look at the positive infinity part. All right, so sine of x, the limit as you approach infinity of sine of x, this thing, all right, is always going to be less than or equal to 1. Highest value you can get for sine is 1. If we just think about the biggest this can get or the smallest it can get, all right, is going to be 1 or negative 1. Okay, so it's going to be bigger. This will be bigger, but negative 1 would be smaller. All right, over x. So sine, no matter what you put into sine, the biggest is 1, the smallest is positive, negative 1. So to do that, divided by something that gets really, really, really big, this is really just 1 or negative 1 or smaller, divided by something really, really, really big, well, yeah, that's going to give you 0. Right? We talked about how 1 over x gives you 0. Right? And this goes to 0, that means this goes to 0. That's what we call the squeeze theorem. All right? We learned that way, way, way back when with limits, right? With this exact limit, actually. We did it at 0, but the idea still works, okay? All right, for this wonderful expression, all right. All right, the negative side, we got positive 0.44, positive 0.49, 0.499. All right, I would say that is about 0.51 half, right? As we switch to the positives, looks like 0.56, 0.505, 0.5005. Well, I would say that looks like it's again going to 0.5. So we do have a horizontal asymptote here at y equals 0.5 or 1/2. Cool. So if I graph that, we should see how the right side of this graph does approach that, the left side of the graph does approach that, and it doesn't really go past it. All right, we don't have something else weird going on. All right, but algebraically, how can we do this limit? If I try to do the limit as x approaches infinity of 3x plus 1 over 6x minus 5, and in my head, if I just plug in infinity, let me show you what happens. All right, if I put infinity here, that'd be 3 times infinity. Well, 3 infinities is still really big. Add 1 and I got infinity. I'm going to have a really, really, really big number. Over 6 times infinity is infinity. Take away 5, still infinity. All right, so I can't just kind of plug in a big number algebraically in my head and come up with an answer. It's not quite like these where I had just a constant number on top divided by something that grew and grew and grew, or just a 1 on top and it grew and grew and grew. All right, this one, the top and bottom are both growing. So we have a way to do this. The idea is when it's polynomials, find the highest power of x in the problem. All right, the highest power of x is just, it's x. There's no x squared that's cubed or something like that, like the next one. So find the highest power of x. It is just regular x. You then divide every term in the entire problem by that highest power of x. Now, 3x over x is just 3. 6x over x is just 6. Now, these two don't reduce. But now when you plug in infinity, this thing becomes 0. This thing, 5 divided by something really big, becomes 0. So now we are left with, algebraically, we haven't broken any rules. We're left with just 3 over 6, no more variables. And that's where this 1/2 is coming from. All right, so algebraically, when you're trying to do these things, and it's polynomials, you can just divide by the highest power of x that you see. Okay, so I trust that you can do the table. All right, let's see if we can do this one algebraically. If I try to do the limit as x approaches infinity, now up here, I guess I should add the negative infinity would produce the same thing, right? All right, these would be 0 still, and there's no x values here, so that's why it's still just positive 1/2. I don't need to do the negative one. All right, so as we do infinity here, I would wind up with like 3 times infinity squared on the top, so infinity over infinity. All right, so I can't really do that. So I divide by the highest power of x I see. So 3x squared over x squared plus 2x over x squared plus 4 over x squared. I'm sorry, x cubed. I need to do cubes. Cubes the highest power I see. I reduce 3 over x plus 2 over x squared plus 4 over x cubed, 2 minus 5 over x plus 1 over x cubed. All right, now when I plug in infinity in my head, I get 3 over infinity. That's a 0. 2 over infinity squared. That's a 0. 4 over infinity cubed. That's a 0. On the bottom, I have just a 2. 5 over infinity is a 0. 1 over infinity, that's a 0. So I wind up with 0 over 2 or 0. Right? And you'll discover that this function, if you do the limit form or the table form, you will get 0 for both sides. Now, will it matter if it's positive or negative here? Well, no. If I put negative infinity into all those ideas, I still just have this 2. There's nothing else I have to worry about. All right, so here, let's check it out. If I plug in infinity, I've got variables on the top and the bottom. I'm going to get infinity over infinity. So let's try it again. Highest power of x I see is x squared. Reducing all right, so reducing this thing, or plugging in infinity, really, I've got 0, I guess 5 plus 0 plus 0 over 0 plus 0. Ooh, yikes, I've got 5 over 0. Okay, so by plugging in infinity, or I guess by dividing by the highest power here, I wind up with something like this, 5 divided by 0. All right, so this does kind of cause some issues. Now, when that happens, we have one of a couple choices that can help us out. All right, the first thing we could do, usually when the top of a function is bigger than the bottom, one option that you could do is synthetic or long division. that's an option that you can do to reduce it down. Hopefully you remember that from way back when in Math 171. The other option is to kind of just think about this, what's going to happen. All right, actually, let's try it this way. Instead of dividing by x squared, because that produced zeros on the bottom, what if we divide everything just by an x? 1 less power. So it would be 5x plus 6 plus 1 over x. 3 plus 4 over x. That's a good idea. All right, so instead of doing the highest power, because I got something weird, I do one less. I do the highest power of just the denominator. All right, and so what that produces when we do infinities, I would have on the top 5 times infinity, and that's like infinity, plus 6 plus 0. On the bottom, I'd have 3 plus 0. So I have infinity plus 6, that's infinity, over 3. Well, that just means infinity, okay? So as I plug in infinity, all the things cancel except for this infinity on the top. Infinity plus 6 is infinity, divided by 3 is positive infinity. So the right side here is going to approach positive infinity. All right, if I switch and do negative infinity, not a whole lot changes. All right, but if I make this negative, so that's negative, really as I plug in these negative infinities, the only spot it's really going to matter is this first one. All right, all the other ones will just make zeros. 1 over negative infinity is still 0. 4 over negative infinity is still 0. But it just means that my final answer here on this side will be negative infinity. Let's see if our graph agrees with us. All right, so looking at this thing, as you go really far to the right, what happens to that function? Yeah, we go up to positive infinity. As you go really far to the left, what happens? Yeah, we go down to negative infinity. All right, I agree. Now, this thing we would have is called an oblique asymptote or a slant asymptote. And the way you find the equation of that is by doing long division, like what you learned way back in Math 171, as I was talking about. All right, next one. Let's take a look. All right, we could, as I said, we could do just the tables. All right, we could do those. All right, I'm not worried about those, but we could do them. All right, so let's try to do this algebraically. All right, so as we do the limit as x approaches negative infinity, actually, let's take this and then let's look at the graph. 2 plus 3e to the x. So this one's a little bit different. 1 minus 12e to the x. All right, so I'm seeing 2 horizontal asymptotes, okay? They level out, that's good. So let's figure out how to find them. All right, if we just plug in negative infinity, let's see what would happen. All right, so it would be the limit as x approaches negative infinity, 2 plus 3e to, technically it would be like a negative infinity here. 1 minus 12e to the negative infinity. Okay, so the idea, and I want you to think about this, this e now has a negative exponent. All right, what happens to negative exponents? Well, we should know they move to the bottom and become positive. Same thing here, this e to the negative infinity becomes a fraction. It moves to the bottom of that fraction and it becomes a positive. Well, what happens to 3 divided by e to the infinity? E to the infinity is very, very, very large. All right, so this is going to become 0. And this on the bottom, 1 minus 12 divided by e to the infinity, will just become 1 plus 0. So our horizontal asymptote on the left should be at 2. Let's check it out. Y equals 2. And look at that. That's a perfect match. All right, we've got our horizontal asymptote lining up with our function. All right, let's figure out what happens on the right-hand side as we do x goes to positive infinity. All right, if you just try to plug in infinity, it would be, what, 2 plus 3e to the infinity, 1 minus 12e to the infinity. That would be infinity divided by infinity. That's just not going to work. The top is getting big, the bottom's getting big. Doesn't quite work that well. All right, so let's employ that method we've been doing. Let's divide by the highest thing we have, the highest power we have, which in this case is e to the x. So we are going to divide everything by e to the x. Now what's going to happen when we do this is that 2 over e to the x is going to stay, but this is then going to become 3. 1 over e to the x is going to stay, but now this becomes minus 12. Now when we plug positive infinity into here, 2 over e to the infinity, that's 2 over infinity, which is 0. 1 over e to the infinity is 0. So we wind up with 3 over negative 12, or negative 1/4. And let's check that out, how that looks on our graph. And look at that. I would say that that's a pretty good horizontal asymptote there. And your table should line up with that idea. All right. So hopefully we have a decent idea here of how to do limits to infinity. Some of them will produce answers of infinity, all right, like we saw with this one, all right, or negative infinity. Some of them might have 2 asymptotes. All right, weird things happen for positive infinities compared to negative infinities sometimes. All right, and some of them will have the same asymptote on both sides. All right, a 0.5 and a 0.5. All right, it's your job to kind of play with the algebra a little bit. My suggestion: divide by the highest power of x you kind of see, and figure out kind of what happens. Allow things to become zeros in the problem. All right. With that, good luck on this. Let me know if you have any questions.